Good evening. This is CS150 Lab Activity 2 for my group, Antonio Lim C. I think it's Group 8. And this basically for this lab session, we're going to be looking at Return to Lab C. So first off, what is the Return to Lab C? What is the Return to Lab C attack? So the Return to Lab C attack is an attack that begins with a buffer overflow that uses the code that is already visible to the target program. So something like libc. And unlike normal shellcode attack, like last week when we did a normal injection, the injected shellcode in return to the libc does not contain code for spawning a system shell. So essentially, what this return to libc exploit does is it looks for the memory address of system and the string bin/sh, which is also part of libc, and it jumps to system, and via that it uses this function call to be able to spawn a shell. So that's the summary of that. So for our task 1, we're going to be finding the addresses of the libc functions. So first and foremost, these are the preliminary steps that we have to do, such as disabling ASLR, so the address space randomization. So this is just to disable the countermeasures against buffer overflow so that we can conduct the attack. And then next is we're going to be compiling the vulnerable program retlib.c, and we're also going to be compiling it with the -z no xx stack and fno stack protector and the buffer size given, which was 50. So the other operations are pretty standard, such as sudo chown root and sudo chmod 4755. And next is we're going to be printing out the addresses of the libc functions. So how we did this was we inserted the breakpoints and ran the program, and with that we were able to identify the system and the exit. System is 0xb7e58190, and the exit is 0xb7e4b1e0. So these are the addresses of system and exit. And now for the second task, we're charged with putting the shell string into the memory. So the way that we do this, to be able to find the address of bin/sh, so we use the Gnu Debugger, and with the Gnu Debugger, we were able to use the find command. And with the find command, what we did was we used the system address, so there, as a starting point, and then we added 9999999. So basically a very large offset in order to find the address for bin/sh. And with this, we were able to actually find the resulting address for /bin/sh, which was 0xb7 f79344. So we see that over here. And now for task 3, which is basically exploiting the buffer overflow vulnerability. So here is actually our exploit.c file. So as you can see there, this is the program that's going to be able to generate the bad file and allow us to conduct the return to libc attack. And then so with this, we inputted the 3 addresses of the bin/sh, the system, and the exit. The values were actually gotten. So from here, we got the bin/sh. In here, we got the system and the exit. So we basically just inputted it in the exploit.c file. And so in here, so we were able to get, now that we got the addresses of the system, exit, and bin/sh. So this is basically when we disassemble the buffer, and here. So the values for the buffer indices that we got, so x is 32, y is 24, and z were 28. So we determined this by constructing the stack frame from the disassembled code. So from the disassembled code of the retlib.c. And to do this, so we compiled the retlib.c and then started the Gnu Debugger, GDB, and with this as buff, that's how we got the generate the corresponding assembly code. So in here, from this diagram, this is the illustration of the stack generated by the code, and then we assigned a buffer size of 24 for the system function, since buffer 40 is 24 bytes away from the return address, and we overwrite the return address by calling the system function. And then after the system function was called, the stack, it now points to the exit function, and that's why we added another 4 bytes, which when added to the previous 24 bytes, so that gives us a total of 28, and that is the buffer size of the exit function. And then lastly, the /bin/sh, when it enters the stack, so this is actually like an argument that will be passed into the system function, and we add another 4 bytes and give that a buffer size of from the 28, so 28 plus 4, that gives us 32. And with that completes our return to libc attack. So here, obtaining the root shell. So after we were able to get all the address in the buffer indices, this is what happens when we compile and run the code. And as you can see, we were able to obtain the root shell. So this is the first variation of the attack. So with this one, you can see that this is the code that we used, and in this one, the exit function is not necessary when obtaining a root shell. However, as you can see here, we noticed that the exiting of the shell resulted in the segmentation fault core dumped. So that's from the variation 1 without necessary use of the exit. And now this is the attack variation 2, wherein when changing the file name, it resulted in the attack being unsuccessful, because when you change the length of the file name, it changes the addresses as well, and that's why this would cause the program to incorrectly point to the wrong address instead of the proper bin/sh address. And you have to remember that we got the address of bin/sh by using the find method of the GDB. And though this makes the code work, because libc is a shared library above the heap and is not affected by the file name. So for task 4, so basically this is looking at what happens if we turn on address randomization. So when we turn on address randomization, as seen here, run the program with the necessary countermeasures there. So we can see that when we turned on the address randomization, the program resulted in segmentation fault, core dumped. And the reason why is because the addresses of the system, the exit, and the bin/sh are not constant, because that's what address randomization does. They're not in the same place, they're constantly being moved around. And because of that, we can't just, the probability of us being able to hard-codedly guess it drops. And another thing is that it does not, however, affect the buffer indices though, since the buffer indices are not reliant on the addresses themselves, but they do rely on the code itself, which is not changed with address randomization. So this is for task 5, the additional task, sorry. So we did not have no need to do this in the VM. So this is basically discussing if it is possible to chain multiple functions without arguments. And this is actually possible by using or utilizing return-oriented programming, ROP. And what this does is basically it's a computer security exploit technique, which chains together snippets of assembly with stack control. Each of these code snippets end with return instructions. So, as you can see here, in this one, this example, we replace the return address with the function without arguments. And when the function returns, it calls the noarg function, and the idea is to actually overflow the stack and return the return address. So that's with return-oriented programming. So with that, we're able to chain multiple functions without arguments. And now the second part of task 5 was to discuss whether it was possible to chain multiple functions but with arguments now. And to answer this, yes, for functions with arguments, we can do ROP chaining as well. So if we were to do that, we could do something like what is shown below in this one. So when a function is called, all the registers have to be saved. But before the function returns, all the previous registers get restored. We replace the return address with a function popret, right? And what it does is going to pop the argument value that we need. In this case, 1. And off of the stack, in order to call the function, call with 1. So when the stack pointer moves up, it will turn to the next thing in the stack, and then we call the function call with 2, as seen there. So this concludes our lab 2 for CS150. Thank you.